All right, so let's continue from where the video ended. Sorry about the abrupt ending. I didn't time it well. But this is the proof of the maximum principle for the numerical problem. So we are going to assume that the numerical solution attains its maximum value at an internal point, and we said let the internal point be this. And now we can let U star represent the maximum of the rest of these points, okay, in the stencil. All right. Okay. So if this is the case, and you go back to equation 3, that is the theta scheme. I just replace, the red by the internal point, that is our maximum, and then I have the blue ones are just the rest of the stencil. Now, because the coefficients of these guys are non-negative, okay, if I replace each of these blue elements, these blue variables, by the maximum, which is U star, then I'm going to get the left-hand side must be less than or equal to what is on the right-hand side. Okay, that's because these coefficients are non-negative. And now I'm replacing each of these by the maximum, and so this quantity is true. I can factorize U star out, can simplify it to this, which implies that the left-hand side is less than or equal to this. I can cancel out what is in brackets, and this shows that Uj into n plus 1 must be less than or equal to U star. Okay, good. So keep this in mind. This is less than or equal to this, but remember that we assumed that this Uj n plus 1, which is an internal point, is the maximum that is attained internally. If it is the maximum, then of course it has to be greater or equal to what? U star, where U star is the surrounding nodes. So we just showed that it is less than U star, but by assumption we know that it has to be greater than this, therefore it has to be equal to this. Okay, so this implies that the maximum must also be attained at each of the neighboring points with a non-zero coefficient. Okay, so in other words, the maximum is not only attained here, the maximum could be attained at a neighboring point, let's say this guy. Okay, and now the proof is that if I do the same thing and assume that the maximum is attained at an internal point, and now the internal point is this guy, okay, I can go through the same argument and show that, well, it's not just this guy, there's a point here where the maximum is attained. And so you have a series or a sequence of points until you reach a boundary point, which shows that the maximum is attained, okay, is also attained at a boundary point or initial point. And that is what is written here. Okay, so the maximum is also attained at a boundary point. So that gives you a proof for the right hand side of, if you go back, of the maximum principle. So what we have proved is this side of the equation. Okay, your exercise is to show that this side is also true by following a similar argument. Okay, so we have shown this. So the first exercise is that present an identical argument to show that the minimum, which is U min, is also attained at a boundary or initial point. So write up your solution, your argument, and then you post it on Sakai. I'll try to set up something on Sakai, or you can email it to me. Take a picture, you can convert it to PDF or something, and then send it to me. Okay, so that is about the maximum principle. Okay, so in the next video we'll look at general boundary conditions. Okay, general boundary conditions. Specifically, we want to look at derivative boundary conditions, because that is important. So far we've been looking at the Dirichlet boundary conditions, where the value of the solution, all right, is given at the boundaries. And now what happens if you have derivatives at the boundaries, so-called Neumann boundary conditions. So in the next video, that is what we'll be discussing. Okay, so I'll stop this so that I'll start a new video with it.